Yeah, I'm going to talk about some results from the geometry of surfaces embedded in R3 with non-zero constant mean curvature, and all that I'm going to talk about is joint work with Bill. Okay, so this is a brief outline of my talk. I will begin by giving a brief introduction to the theory of constant mean curvature surfaces, CMC surfaces, and I'm going to due to the audience, I'm going to try to go very fast, but it can't hurt anyway. Then I will provide some historical perspective that's probably so that we can appreciate better the results that Bill and I proved. Then I'm going to talk about the main results, and then future directions. I'll talk about some problems that Bill and I have already been working on, and some questions, some questions that we haven't tackled. Okay, so we have a surface in R3, so we know that when we take the derivative of the normal vector, so minus that is A, which is the shape operator, and that's the map that goes from the tangent space to the surface into the tangent space of the surface. And this so this shape operator is what contains the information on how the surface sits in R3. So if one wants to study the geometry of a surface, then looking at the shape operator can give a lot of information. So the eigenvalues of the shape operator are the principal curvatures. The average of the eigenvalues, or half of the trace of A, is the mean curvature. And the norm of A, which is the square root of the sum of the squares of the eigenvalues, is the norm of the shape operator. So a very satisfying way of describing the geometry of a surface is, for instance, to bound the norm of A. Because when one bounds the norm of A, then you're bounding the derivative of the normal. And if you bound the derivative of the normal, then that means that the normal cannot change too fast, right? Because its derivative is bounded. So that provides good information. I will explain a little bit better later on what bounding the norm of A implies. But so let's look at the so what does it mean to bound the norm of A then? Well, we have the Gauss equation, right, which gives a relation between the norm of A, the mean curvature, and the Gaussian curvature. And so when H is constant, bounding the norm of A is the same as bounding the Gaussian curvature. So for this reason, this estimate, we refer to this estimate, so this estimate on the norm of A as curvature estimates. Okay, so an example, when a surface is given as a graph, then in order to express the mean curvature, we have this quasi-linear elliptic PDE, and this is the prototypical quasi-linear elliptic PDE. So, and it enjoys property like the maximum principle or the Harnack inequality, for instance. And again, if a surface is given as a graph, then we have this bounds for the norm of A that depends on the Hessian and the gradient. So which means that when the gradient is bounded, the norm of A is pretty much the Hessian. Okay, so what is a minimal surface? A minimal surface is a critical point for the area functional, and this is the same as asking for the mean curvature to be identically zero. We know examples of minimal surfaces. There is the catenoid, there is the helicoid, and then there is the plane, but it was very hard to find a picture. So the key example to keep in mind throughout this talk is the helicoid. So the helicoid is the surface that one obtains if I take this remote and I lift it and rotate it at constant speed, that's the surface that we obtain. And this is going to be a key example throughout this talk. And then what are constant mean curvature surfaces? Well, so minimal surfaces are constant mean curvature surfaces, just a very special kind of constant mean curvature surfaces. But in general, constant mean curvature surfaces are a critical point for the area functional under variations which are set to preserve the volume. And this condition turns out to be equivalent to h identically constant. So if when a surface is closed, then it makes sense to talk about preserving the volume. When it's not closed, then it still makes sense, but the volume that one considers is you take a point which is not on the surface and you consider the cone over the surface. Examples are the sphere. These are classical examples: sphere, cylinders, and the Delaunay surfaces. Okay, one last thing. Minimal surfaces and CMC surfaces in general appear in nature. That somehow makes the subject even more interesting. If we take a closed wire and we dip it in soapy water, the soap film that forms, that's a minimal surface. And if we think of a soap film, the air pressure on both sides of the film is constant and equal to the same constant. If we change the pressure on one side, say by blowing air on that side, then what we obtain is a soap bubble, and soap bubble are general constant mean curvature surfaces. Okay, so this terminates the introduction, and now a little bit of history. So in this slide, we're going to study the closed CMC surfaces in R3. So closed being compact without boundary. Okay. The first thing that we can say is that such a surface cannot be minimal, right? Because coordinate maps are harmonic on a minimal surface. That means that they cannot achieve either a maximal or a minimum at an interior point. But if the surface is closed, then they must achieve a maximum or a minimum at an interior point, giving a contradiction. So M cannot be minimal. And then there is this very important result by Hoff. He proved that if M is genus 0, so if it is topologically a sphere, then it must be, in fact, a round sphere. So after this result, Alexandrov proved that if M is embedded with no restrictions on the topology, then again M is a round sphere. Okay, and in proving this theorem, actually he uses the maximum principle in a very clever way, which is now called the Alexandrov reflection principle. And so after these two results, actually there are many years where people cannot find examples of other closed CMC surfaces besides round spheres. So a conjecture was born called the Hoff conjecture that said that the only closed CMC surfaces in R3 must be round spheres. So this is called the Hoff conjecture, but actually Hoff himself never made the conjecture. He actually asked the question. So it took about 20 years for Wente to prove that there exist other CMC surfaces. His paper was counterexamples to the Hoff conjecture. And so the second one is half of a Wente Tor. Somehow it's you open it up. That's the idea. And after these examples by Wente, there are many examples of closed CMC surfaces, starting from the examples of Capouleias, but then many others. Okay? So these two slides provide a snapshot of the geometry of closed CMC surfaces in R3. And so they lead naturally to the following question. So what happens when one removes the compactness hypothesis? So is the round sphere the only complete simply connected surface embedded in R3 with non-zero constant mean curvature? Okay? And of course all the hypotheses are necessary, because if the surface is not simply connected, then we have cylinders, and if the surface is not embedded, we have Smith surfaces. Actually, he classified this constant mean curvature surfaces. Okay, and so the answer to this question is yes, and this is some of what I'm going to talk about, and this is joint work with Bill. Okay, so the theorem is the following. So round spheres are the only complete simply connected surfaces embedded in R3 with non-zero constant mean curvature. And this was proven by Meeks for properly embedded. And so this result, together with the work of Colding-Minicozzi and Meeks and Rosenberg, who studied simply connected CMC surfaces embedded in R3 with mean curvature 0, so minimal surfaces. So together with their result proves that the only complete and simply connected CMC surfaces embedded in R3 are the plane, the helicoid, or round spheres. So the question, actually, the question that was asked is rather classical and simple to understand, but so the problem, when you remove when you remove compactness, then you have, when you move the hypothesis closed, then we have to study the geometry of surfaces which have boundary, and somehow the presence of boundary makes things more complicated. So while the question is very classical, the study that Bill and I had to do is deeper than the question itself. So we'll see some of the results. Okay, so I'm going to introduce a definition, and this is just to make the statement of the theorem a little shorter. So I'm going to call a one disk a simply connected surface embedded in R3 with constant mean curvature 1. Okay, so possibly with boundary. Actually, more often than not, it will have boundary. So the first result that we prove is this radius estimate. We prove that if you have a one disk, then if you pick a point on the one disk, the distance from that point to the boundary cannot be too big. So somehow this embedded simply connected solid bubbles cannot be too big. Okay, and so this is the radius. So the radius is bounded by a universal constant. So universal meaning the constant r, well, does not depend on the surface. Otherwise, there would always be a constant, right? And this radius estimate immediately gives the answer to the question. Immediately gives the uniqueness of the round sphere under the previous assumption, because so if M is a complete one disk, then the radius estimate implies that M is compact. But then, because of the assumptions that we have, M is an embedded sphere. And then at this point, you can use your favorite result. You can either use Alexandrov result because it's embedded, or you can use Hopf result because it's a sphere. In either case, M is a round sphere. Okay? So this radius estimate is the key to prove the uniqueness of the round sphere. But then again, in order to prove the radius estimate, we have this curvature estimate. Okay? And again, curvature estimate are important because they tell you that the surface cannot, where you have a curvature estimate, where the second fundamental form is bounded, the surface cannot bend too sharply. So what this theorem is saying, there exist two constants, universal constants, delta and c, such that on a one disk, if we have a point which is sufficiently away from the boundary, the curvature as that point is bounded by that universal constant. Okay? And so we use this result to prove the radius estimate, and I'm going to give you an idea on how that's proven now. Okay, the first step is, so we argue by contradiction. We argue by contradiction, and we assume that there isn't such a bound on the radius, so we have this sequence of one disk with radii going to infinity. Okay? And then we have the curvature estimate, which tells us that away from the boundary, we have bounded second fundamental form. So these are our disks, okay? And say this is the center. Say they contain the origin, just for simplicity. And this is n, okay? And then if we stay lambda away from the boundary, I think I use capital lambda, right? If I stay lambda away from the boundary, then in here the curvature is bounded. Okay, so here the norm of A is bounded by a constant C. So I can just replace, I throw away this this neighborhood of the boundary, and I just replace the sequence with one disk which have uniformly bounded second fundamental form. And this is still going to infinity because n is going to infinity. Lambda is a fixed constant, so n minus lambda is still going to infinity. Okay. Now, what does it mean? So the question is, what does it mean to have uniformly bounded second fundamental form? So again, so in general, if you have a point on a surface, we all know that the surface, there is a neighborhood around that point which is graphical over the tangent space at that point. Okay? That is always true. However, this neighborhood depends on the point in general. Okay? So if we have that the norm of A is bounded, then the derivative of the normal is bounded. So the normal cannot change too fast on the surface. This too fast depends on C. But anyway, there is a fixed size neighborhood now which is graphical. A fixed size neighborhood of each point, which the size of the neighborhood depends on C, but it is graphical. Okay? So, and then what do we have? Well, we can say a little more. We can say that actually this graph, once we know that we are on this neighborhood which is a graph, we can say, for instance, that the norm, the C2 normal view of these graphs is uniformly bounded by a constant which depends on C. Okay? And this is already very good information, but somehow usually this information is not enough, because suppose now we have a sequence of graphs which satisfy this condition, right? If we use Ascoli, we can find a convergent subsequence. But because the normal view is bounded in C2, this sequence of graphs would converge in C1. And that's not good enough, because we're interested in quantities like the second fundamental form, the mean curvature, and these quantities have two derivatives. So we want the convergence to be C2, but then we have that this, the CMC graph satisfies this equation. So Schauder theory actually gives that the C2 alpha norm is bounded independently of the point, and that's better. Okay. So this is why having the soup of the normal way bounded is good. Okay. Okay. Now let's go back to what we had. We had a sequence of one disk with radii going to infinity and normal way uniformly bounded. Then we can say that a subsequence of such disk converges C2 to a complete embedded CMC equals 1 surface and with bounded curvature and G 0. Okay, so now that I told you what happens when the second fundamental form is bounded, it's easier to see what I mean by converges C2. So the second fundamental form uniformly bounded means that if I take a ball in R3 and I look at my surface intersect this ball, all I see is graphs, not necessarily one. Let me just write one, but not necessarily one. So each time I see a graph, UN, and since I have a sequence, these graphs are bounded. So the norm of this sequence, the C2 alpha norm of this UN is bounded, so I can extract a convergence subsequence. So this UN converges to a graph, say U infinity, and then I can apply a prolongation argument to get a complete surface. Okay, the convergence now it's C2, so the mean curvature converges. I mean, the mean curvature is 1 in the limit. The curvature is bounded. So a topological argument, it's pretty easy to see that given that the elements of the surfaces are disks, then the limit surface has to have genus 0. Okay? And then what happens, so embedded, that is all embedded. So let's say why embedded is in quotes. So in the limit, I certainly cannot have a transversal intersection, because if the surface in the limit would intersect transversally, then some elements in the limit must have intersected transversally, but the elements in my sequence were embedded. So that would be a contradiction. So what could happen though, and that's why the embedded is in quotes, is that in the limit the surface intersects transversally, and you have to think about it like tangentially. Thanks. Think of two spherical caps, a sequence of spherical caps, right? They are embedded, but in the limit they might touch at one point. So this could happen, but for all intents and purposes, actually, these surfaces are embedded. Everything works anyway. Okay? But embedded is not enough. So embedded just means that there's no self-intersection, but what we want to show is that actually M is properly embedded. So we also want to say that if something goes to infinity on the surface, then it has to go to infinity in R3. So nothing accumulates in R3. Okay? So when I said, so again here, I said it was a bit, I simplified the picture. I said in one ball there is one graph. I mean, I draw one graph, but eventually there could be, the number of graphs could grow to infinity, right? Okay? And eventually in the limit, I might not have one graph, but my surface can have infinitely many graphs in this ball. Okay? So perhaps I should index, I have U1 infinity, U2 infinity, and then a sequence of graphs accumulating somewhere. Okay? U n infinity. Okay? And then you treat this as you were treating the sequence, pretty much. So if you look in this, even if, but the second fundamental form is bounded, so if you look in an extrinsic ball, you still have graphs. So what you have is called the lamination. Okay, and I'm sorry. In the limit, if you look at the closure, if you look at the limit of this sequence of graphs, again arguing like before, you get a complete surface with constant mean curvature equals 1. So the argument is exactly the same as before, but instead of having a sequence now, we have to look at the closure of the surface. Okay, but it's not hard to see that the universal cover of the limit surface is stable with constant mean curvature 1, and such surfaces do not exist. Okay, so indeed our limit had to be properly embedded in quote in R3. Okay, and then we apply this result if under this assumption. Yeah, but I'm still going to write. Under these assumptions, we still have that we can say that M contains a Delaunay surface at infinity. So if you take a sequence of translation on our surface, eventually what you see is a Delaunay surface. Okay, Delaunay surface where CMC surfaces of evolution, and they look like this, right? And this result was proven by Kolar, Kastner, and Solomon for properly embedded surfaces, CMC surfaces with finite topology. But actually, in this, we need the full generality of our result. Okay? And once we have this, it's not hard to show that a Delaunay surface cannot be a limit of one disk. And so Delaunay surface, this, and so suppose it was a limit. You have the Delaunay surface here goes to infinity, right? But and suppose that this is our CMC disk with boundary here. Then using again the Alexandrov reflection principle, actually one can show that the disk coming out of this. So this circle bounds the disk because our surface is simply connected, and this disk cannot be too big. In other words, you cannot have long fingers. If the boundary of a CMC disk is contained in a ball of radius 1, say, then the disk itself is contained in the ball of radius, let's say 3 over h, just to be on the safe side. That's not sharp. Okay, so you cannot have that this disk goes all the way to infinity and becomes this Delaunay surface. Okay? That's a good.
Reflection principle says it would be graphical. There are height estimates for graphs.
It cannot. No, but he asked another question. That's a good point.
What did he ask?
It cannot wrap around because otherwise the limit would be stable. I was.
It has to be close to the Delaunay surface. Yeah.
It cannot have infinite multiplicity. The convergence.
It's a compact disk and it has to be close to the Delaunay surface for it to exist.
But what is saying? So there is another argument to rule that out, which I was shoveling under the rug. But you're right. So that cannot happen either, but because of another reason, right? Because otherwise the limit, if that happens, then the limit is stable, and again that can't happen. Okay, now, that's a very good point. Okay, so there was a contradiction, and then that ends the proof of that. And now we want to say, so that this is again this is the intrinsic curvature estimate. Again, if you have a point which is sufficiently away from the boundary, then we have the second fundamental form is bounded, and now we want to take a look at the proof of this result. Before, let me point out that this estimate doesn't hold for minimal surfaces, right? If you rescale a helicoid you get a sequence of minimal disks with arbitrarily large second fundamental form. So the second fundamental form blows up on the axis of the helicoid. And this rescaling argument doesn't work in the non-zero CMC case because rescaling changes the mean curvature. Okay? So the constant that we put, so I'm stating the result for constant mean curvature equals to 1, but by rescaling argument you can get all non-zero constant mean curvature, and the constants depend on the mean curvature. Okay. Okay, so the strategy, so there are two main ingredients, two main theorems that we have to prove in order to prove the intrinsic curvature estimate. So the first is a chord arc bound, which was done by Colding-Minicozzi for minimal surface. For minimal surfaces. So in general, we know that if we have 2 points on a surface, then the distance, the extrinsic distance between these 2 points, so the distance in R3 between these 2 points is always less than the geodesic distance. Because, you know, when you travel on the surface, you travel more than traveling on a straight line. Okay, chord arc bound means that if we're living on a one disk, we have somehow a reverse property. So we have that if we have a geodesic which is too long, then this geodesic, which is sufficiently long, again, these are universal constants, then it has to leave a ball of radius 1. Okay? So it's not exactly a chord arc, it's not exactly the reverse property because the surface could come back. I mean, the geodesic could come back into the ball of radius 1, but at least what we know is that when we intersect, if we take this component, the bound, it has the boundary on the ball of radius 1, and then if you throw away the rest, then you get something which is contained in the ball of radius 1 with boundary in the ball of radius 1, in the boundary of the ball of radius 1. So this is the first, the first step, and so the upshot of this theorem is that it gives you a relation between extrinsic distances and intrinsic distances. So now instead of proving an intrinsic curvature estimate, we could prove an extrinsic curvature estimate. So a curvature estimate which depends on extrinsic hypothesis, and supposedly that's easier to do. So this is exactly what we do. So this curvature estimate is just like the estimate before, but now we have this extrinsic hypothesis that the boundary of our surface is in the boundary of the ball of radius 1. Okay? So again, let me review how one proved the intrinsic curvature estimate. So the chord arc bound says that when we intersect M with the ball of radius 1, we get a compact component which has boundary in the ball of radius 1, and then we apply the extrinsic curvature estimate to this component. Okay? Okay, so far I've talked about results for disks. Okay, actually these results can be applied, these are local results that can be applied to study also the geometry of complete non-zero CMC surfaces embedded in R3 with finite topology. So the first thing that we prove is that such a surface has bounded curvature and it is properly embedded. So again, properly embedded meaning that this something that goes to infinity on the surface goes to infinity in R3. So this business here that the surface accumulates somewhere cannot happen. Okay? And then we have that if M has more than one end, if M has more than one end, or otherwise it's a round sphere, this is a slightly more general result than the uniqueness of the round sphere that I mentioned before. And then one can say stuff about the end, so how the surface behaves at infinity, but I want to point out that the key point here is to prove properly embedded, because once you have properly embedded, then this was done by, the study of a properly embedded CMC end, annular end, was done by Meeks and by Corva, Kastner, and Solomon. Okay. So the first bullet is the main bullet. Okay. These are just some examples of constant mean curvature surfaces. Genus 0 and 3 ends. Genus 0 and 4, 6, 7 ends. Okay. Okay. So then we shifted our problem. So now our goal is to prove extrinsic curvature estimates. So curvature estimates with the assumption that the boundary of our one disk lives in the boundary of the ball of radius 1. Okay. So how do we do that? Okay. By contradiction, suppose that the curvature blows up. Then we need to study the geometry of the surface at points where the curvature is arbitrarily large. Okay? So the first step is to prove that the surface looks like a piece of helicoid, a small CMC1 helicoid. This is so the way to see this is that, again, rescaling on the scale of the surface, rescale on the scale of the second fundamental form, in the limit one obtains a helicoid. Okay? If you take our surface and you rescale by the norm of the second fundamental form, in the limit you get a helicoid. So that means that on a ball of radius 1 over the second fundamental form, the surface looks like a helicoid. Okay, you blow up, you see a helicoid, then if you scale down, what you had to be looking like a helicoid. So this is very valuable information, but so I'm going to call this piece that looks like a helicoid, small CMC1 helicoid. So this is very valuable information, but unfortunately it's on a very small ball. Again, so the size of the ball where this happens is proportional to 1 over the second fundamental form. Since we're assuming that the second fundamental form is going to infinity, then it becomes very small. Okay? So now we want to go from this local information to a global information. Okay? So this is the next step. So we have this small CMC1 helicoid, and we can attach to it a large minimal helicoid. Large meaning it extends on a fixed scale. Okay? And this minimal helicoid, it is this joint from our surface, from our CMC surface. Okay? You can imagine, so you have this small helicoid that forms. You can imagine this sheath extending, but not CMC, but as a minimal surface. So, and so what's the idea to do that? So using the small CMC1 helicoid, we find a special curve, closed curve, which bounds the disk. Okay, you find a curve that bounds the disk. I'm going to say a little more about this curve. Once you have a curve that bounds the disk, then there is a result by Meeks and Yao, because the Meeks and Yao that says that there exists an area minimizing minimal disks, which has that as boundary. The CMC surface is a good barrier, so we can solve a plateau problem. And then,
but it lies in the complement of the surface.
Right, and it's this joint, yeah, and it is this joint from the CMC surface. And then we use Colding-Minicozzi to study this solution to the plateau problem. So the idea is that, so this special closed curve is chosen so that you doing some analysis, you can show that this solution to the plateau problem spirals a little bit. Okay, so the CMC disks, the small CMC1 helicoid spirals. This solution spirals a little bit. And then there is a result of Colding-Minicozzi that says that once you have something, a disk which is stable, and it begins spiraling, then the spiral extends horizontally. Okay? Okay, so we have this minimal helicoid. We can say that the surface are the CMC surface has points which are trapped between this helicoid. This uses a nodoid foliation, but anyway. So we have points in there, and we can say more. We can say that the points, we can say that in there, the second fundamental form is bounded. And the idea, I mean, again, this is rather technical, but the idea is simple. If it weren't bounded, then you can apply step 1 again and step 2 again, and obtain a large minimal helicoid, which has to be disjoint from what you had before. But because of the nature, because of the geometry of things, it cannot be disjoint, and it would give a contradiction. So the second fundamental form is bounded between the sheath. Okay? And then this gives a contradiction. Why? Well, like before, when the second fundamental form is bounded, then that means that the surface looks graphical between the sheaths. It's more than that. We have that the norm of this graph is bounded uniformly in C2 alpha. We have a lot of these graphs because as the second fundamental form blows up, we have the number of sheaths is increasing. So we can take a sequence, a subsequence converging to a CMC graph. Okay? But this CMC graph is trapped between two minimal sheaths, and these minimal sheaths are very close to each other. And this cannot happen without the CMC surface intersecting the minimal surface. So the idea is the following. So let's replace CMC surface with spherical cap and minimal surface with plane. If you have a spherical cap and you have a plane, then they can intersect tangentially. I mean, they can get close to each other without self-intersecting if the spherical cap is approaching the plane like this, with the concavity facing away from the plane. Okay? But I also have another plane that is facing the concavity, and so as they get close, they have to intersect. Okay? And this contradicts the fact that this minimal graph had to be disjoint from our surface, and that means that the second fundamental form had to be bounded to begin with. Okay? So this proved the extrinsic curvature estimate. And now about the core-dark bound. So the proof, I said that the core-dark bound was proven in the minimal case by Colding-Minicozzi, and as a matter of fact, the steps of the proof of the core-dark bound in the CMC case, and the idea is essentially, the idea of the proof is essentially the one that Colding-Minicozzi gave. Okay? However, one needs this ingredient first. Once you have that, then you can follow the steps of the proof. And this doesn't follow trivially from what they did. Okay, what does this say? This is the one-sided curvature estimate. Again, this was something that was proven by Colding-Minicozzi in the minimal case. It is a generalization of their result, and we use actually their result to prove this. It says that if we have an H disk which is on one side of a plane, but it's close to a plane, then the second fundamental form have to be bounded at points which are close to the plane. Okay? Well, you might say, well, before we proved the curvature estimate without using the assumption of the plane. I mean, so why do we need this? Before, the curvature estimate depended on the mean curvature, and it would get worse and worse as the mean curvature goes to 0. Here we have a curvature estimate which is independent. I mean, which only depends on an upper bound on the mean curvature. So if the mean curvature is going to 0, the curvature estimate still holds. Okay? But in order to prove that, we have to add the assumption that is on one side of the plane. Okay? So this result is stronger than the extrinsic curvature estimate, but we have a stronger assumption. Okay? So what is...
I was just thinking maybe you don't need upper bound of the mean curvature because if you put sphere radius 1, you have radius estimates. So then you can't get close to the origin unless the mean curvature is small, relatively small. Anyway.
No, you're right. Actually, if the mean curvature is
big, you can't
big, then we can just use the extrinsic curvature estimate. Yeah, you're right. So, yeah, sure. So suppose by contradiction that actually the curvature does blow up nearby the plane. Okay? Then, again, using the argument as before, using a rescaling argument, Mn, the surface around the point where it blows up, has to look like a helicoid. Okay? But then, okay, we have a small helicoid. We extend it using Colding-Minicozzi. And what does that give us? That gives that the small helicoid then has to be vertical, because otherwise this extension would intersect the plane. So in this case, we have something more. We have that that it looks like a helicoid, but it's also a vertical helicoid. Okay. So what this tells us, so it tells us that the tangent plane at Pn then is vertical. Okay. If you think of the tangent plane at points on the axis of the vertical helicoid, the tangent plane is vertical. And then we look at the pre-image of the equator via the Gauss map. So we look at all points where the tangent plane is vertical. We look at the connected component that contains this Pn. Okay. So this is a curve on our surface, and we can show that in each point which is on the surface, the surface looks like a vertical helicoid. Okay. So this means that if you look at if you think of the axis of the helicoid, that means that the tangent vector to this curve is always pointing down. Okay? So eventually this curve will intersect the plane, giving a contradiction. Okay, so this idea of the proof of the one-sided curvature estimate for non-zero CMC, and so again it's a generalization of the one-sided curvature estimate for minimal surfaces. It uses as key ingredients Colding-Minicozzi theory. Because once you have that, basically what this theorem is saying, that once you have once the tangent vector to this curve is vertical, it can't stop. So this curve is always going down.
What picture on blackboard?
Think of the vertical axis of the helicoid.
It's the contact surface of the curve that keeps going. It can't turn out.
No. If you do this, the tangent vector is horizontal. It's always going down.
Deep result that at every point, it's a deep result that at every point on the curve, it looks like a helicoid. vertical.
A vertical helicoid, not just a helicoid.
Not just a blow-up point. Every point along the curve is a blow-up point. It's a subtle question. Every point is a blow-up point. That's not obvious. There's certainly blow-up points, but it's not obvious that every point is a blow-up. The entire curve looks like a helicoid. The axis is a
So if you wish this curve, I mean, it is a straight line then.
It's almost
Just
straight.
it just
You
goes
get
down.
the inverse image of the equator in the sphere.
Yeah, but you may have some connected. You have some local pitching and you have some.
No, it can't turn. No, the angle is almost 90, almost vertical, because it's a vertical helicoid. Every point on the curve is a blow-up point. Every point, not just some point. Every point is a blow-up point. So every point is like a vertical helicoid. At every point.
It's not a straightforward argument. It's not straightforward. So it uses Colding-Minicozzi theory. It uses the uniqueness of the helicoid, which itself uses Colding-Minicozzi theory. And then it uses the geometry of minimal and CMC laminations. So there is a so the third bullet does not require Colding-Minicozzi theory. Okay, while the first two bullets do. Okay. So this is what we have done. We have proven that. So we wanted to characterize the round sphere, and we show that we did that by proving radius estimates. In order to prove radius estimates, we proved intrinsic curvature estimates. And the ingredients to prove intrinsic curvature estimates were the corridor bound and the extrinsic curvature estimates, and the main ingredient in the corridor bound was the one-sided curvature estimate. So now, one can ask a question: what can be said about CMC surfaces embedded in now three manifolds? Okay, this is actually rather. I mean, the study of these surfaces in the three manifolds turns out to be very important. Let me just point out some results. Actually, to be more precise, this result using the study of minimal surfaces in three manifolds. But anyway, we have the positive mass theorem, the equivariant loop theorem, and the finite extinction for Ricci flow. This all use CMC surfaces in three manifolds. So what can be proved? So you can prove that if M has positive injectivity radius and N has bounded sectional curvatures, then one has curvature estimate. So the curvature estimate is a local result. If you have bounded sectional curvature, loosely speaking, when you rescale, everything becomes Euclidean. So it's not too hard to expect that curvature estimates hold. And then we can say that if we have something which is complete and embedded in a three manifold, in a manifold with bound sectional curvature, and it's embedded with constant mean curvature, with non-zero complex curvature, then it's proper when the scalar curvature is bigger than epsilon, bigger than 0. This condition, this is just asking for there not to be stable surfaces in there. And then, you use the closure would be a lamination, the limit would be stable, but it can be if you have this condition. Okay? And then, in general, if M is finite topology and N is homogeneous, then M is locally bounded second fundamental form. In H3, one would have an analogous result to the one in R3. Again, the key bullet is the first one, and then the last two follows because the study of properly embedded annular ends have been done already. And then one last question is, what can be said when
kind of get too many.
Yeah, each and we have ends because we and compared to the whole and the financial position like this I mean it's not almost
Okay. Okay, thanks.
I thought cat and grass is back to that. For each of them. Oh, they're slightly different.
it's like categorized in one thing.
Oh, okay. So the cat and aren't absent type different.
Okay, thanks a lot.
Thanks.
And
To a logarithmic term? You have something like a logarithmic term?
What about alpha?
What? Yeah. It's like a logarithmic term.
Like the
So it's a graph over the hard sphere. It's like
but again, let me just point out. Yeah. So thanks a lot. The
R alpha. R alpha. Okay.
Okay, let me just mention that again. The important key is the important point is to prove bounded curvature and properly embedded. Okay. And yeah, and then the rest that needs to be corrected was already done. Then another question is what happens.
Yeah, we proved right. Angular ends are proper. In any hyperbolic three-manifold, that's the harder thing. In any hyperbolic three-manifold, angular ends are proper. If h is bigger than 1. For h equal to 1 or bigger in a hyperbolic three-manifold. Yeah, go back one more time. That's this last question.
If h is 1.
Yes.
If h is 1. The embedded means proper.
Right.
Yes.
Complete and embedded means
Complete
proper. Yeah.
embedded means proper.
We prove that?
We proved that, and we also proved it in hyperbolic three-manifolds. So in fact, that's quite a bit harder.
We proved that, but it's in the slide that says future directions.
Yeah.
Me.
Yeah. So we've written the
We've
paper.
written parts of it. Yeah.
We've written the paper's almost.
Right.
I mean, it's mostly written.
So paper like this?
Yeah, it exists. I'll show it to you.
Can you give me one?
I'll show you the paper. I'll show it to you.
You can look at it.
It's not the final form of the paper. I'll show
Or
you
you
the
can
paper.
improve it.
Yeah, yeah. The hard part is not H3. It's the hyperbolic.
You have estimated curvature for H1.
Right. That's it. The idea is the same as you when
It
you
depends
have
on the injectivity radius. You prove the injectivity radius is positive. The curvature estimate only depends on the injectivity radius.
because as long as yeah,
Yes, sir.
because as long as you
Any surface
have
that's complete and has positive injectivity radius is proper and has bounded curvature. It's the previous slide. Go to the previous slide, Giuseppe. The previous slide, remember this one? The top thing. M has positive injectivity radius.
so all you have to prove is that these surfaces have
positive
positive injectivity radius using this result.
And once it does, then you can.
Maybe you have some. You have some.
No, this is not trying to polish. This is anything with positive injectivity radius. And if you want to put it,
You may have finite surfaces with mean curvature 1.
are they complete and embedded?
Positive injectivity rate.
Zero the injectivity radius goes to zero. No.
A finite number of things.
Anyway, we can talk about it now.
Yeah, there is. Like around
Right, they don't have, right, but they're, right. There are examples which don't have positive
like
injectivity.
Riemann.
That's true. With sphere.
Positive injectivity.
That's true. So you, this says if it has positive injectivity radius, then you get proper.
How can you prove the estimate of curvature in hyperbolic space if you don't have any code?
If you don't have any light.
Any code embedded in it. You don't have embedded.
It's an infinitesimal.
It's a rescaling argument, right?
Rescaling argument.
It's a rescaling argument.
The curvature estimate For example, look at M has finite topology, N is homogeneous. Then you always have locally bounded second fundamental form. In some cases, you can prove it's globally bounded, like hyperbolic space. The conjecture is it always has bounded second fundamental form, but we don't know how to prove that.
Right.
The bottom thing. Right. We think we can prove it, but we haven't proved it for sure. Maybe it's not even true. I think it's true. I think we have a good chance to prove it. I was thinking about it this morning. But anyway, it's a lot of subtle questions.
So the positivity on the injectivity radius tells you that all you're looking at locally, you have disks. And then once you have disks, you have curvature estimate. That's it. And to prove the curvature estimate, again, yeah, it's true we don't have helicoids, but it's a local result. And so you rescale and you do stuff in R3.
But one-sided estimate of curvature in Intrinsic space of Colding-Minicozzi doesn't exist.
No, they have a one-sided curvature. If you look at the paper I did with Harold...
Yeah, think about what they did with Harold, what he did with Harold. They proved properly embedded in using the one-sided curvature estimate.
Look at my paper, the paper with on the minimal lamination closure theorem with Harold. That has a discussion of that.
That is published.
You should get to your final question.
No, well, the final question is just this is very general. Nothing has been done. So this is so if you relax the condition on the mean curvature, what can we say about the surface? And this question is very general. Actually, so the answer to this question in this generality is no to both. Okay, but the idea is if you have some bounds on the mean curvature, L probably it's going to be W1P